Good day, Doctor. We are from Group 5. We would like to present about RLC circuit. My name is Terry Tasapon Kansanok, matrix number 222982. And these are my members, fellow members, Brian, Putri, and Auni. Next slide. So these are our contents: introduction, objectives, mathematical modeling, Laplace transform application, and lastly, simulation and analysis. For introduction, I will pass to Putri.
Okay, for the introduction of RLC circuit, the series RLC circuit has a single loop with the instantaneous current flowing through the loop being the same for each circuit element. Since the inductive and capacitive reactance XL and XC are a function of the supply frequency, the sinusoidal response of a series RLC circuit will therefore vary with frequency f. Then the individual voltage drops across each circuit element of R, L, and C element will be out of phase with each other. And this is defined by IT equal to I max sin omega t. The instantaneous voltage across a pure resistor, VR, is in phase with current. The instantaneous voltage across a pure inductor, VL, leads the current by 90 degrees. The instantaneous voltage across a pure capacitor, VC, lags the current by 90 degrees. Therefore, VL and VC are 180 degrees out of phase and in opposite to each other. And this is the picture of the RLC series circuit. Next, objective of our group RLC circuit is the first one, to develop mathematical model using RLC circuit equation to ordinary differential equation. Second objective is to apply Laplace transform to solve the resulting differential equations. The third objective is interpret the result to understand the impact of various parameters on heat conduction. And the last objective is validate the theoretical result with practical simulations using software tools like Skylab. Next, I will pass to Terry.
Okay, so for math modeling, before going in depth into RLC circuit, we must first know the fundamental of RLC equation. Firstly, we have voltage across resistor represented by R, which is VER equals to IR. Second, we have voltage across inductor represented by L, VL equals to L DIL over dt. DIL over dt is the rate of current change, which is represented by ampere over second. And lastly, before finding voltage across capacitor, we must know the current to the capacitor C. Hence, IC equals to C dVC over dt. dVC over dt is the rate of voltage change, which is represented by voltage over second. Then we can write dVC over dt equals to I over C. After moving the equation around, we can get Vc equals to integration T0 I over C dt plus V0. This V0 is the initial condition of voltage. Then we can conclude that voltage across capacitor is equals to Vc equals to I over C integration of T0 I dt plus V0, sorry. Next slide. So from that, we can conclude and write the voltage voltage total, which is VR plus VL plus VC equals to VT, which is voltage total. We can write that as IR plus LdI over dt plus 1 over C integration of t and 0 I dt plus V0 equals to V0 sin omega t. V total is also equals to V omega sin V sin omega t. After we differentiate with t, we can get the final solution, which is R di over dt plus L d square I over dt square plus I over C equals to V0 cos omega t. This equation is the ordinary differential equation of the RLC circuit. Next. For Laplace transformation, I will pass to Brian.
Okay, we'll explain the Laplace transform application. So there are 5 general steps to solve RLC circuit using the Laplace transform. First, number 1, we write the differential equation. 2, apply the Laplace transform to both sides of the differential equation. 3, substitute the Laplace domain representation of the derivatives and the current into the differential equation. And 4, we find the inverse Laplace transform. And lastly, we obtain the step response of the circuit of the series RLC circuit. So these two are the properties of the Laplace transform. Okay, next. So based on the objective 2, we need to apply Laplace transform to solve the resulting differential equation. So this is an example of general solution for RLC circuit using Laplace transform. So from the circuit, based on the circuit, we are given the equation of V ut equals to RIT plus L di dt over dt plus 1 over C integral from negative infinity to T it dt. Note that VL, VRL, and C are constant. So we reformulate the equation into the other equation. Okay, next step is we apply both sides. We apply Laplace transform on both sides, and we use the properties of the Laplace transform. For example, the time first derivative and the time integral, and next is this represent the initial charge on the capacitor, which is Q bracket 0 positive, and in the end we get this equation V over S equals to RIS plus L bracket SIS minus I bracket 0 positive and plus 1 over C L Q positive 0 plus 1 over C IS over S. Note that the I and Q is the initial charge and current through the inductor and on the capacitor. So next is from the previous equation, we assume that the zero initial conditions for I and Q, which is 0. So we can just remove them and we get the simpler equation, which is V over S equals to RIS plus LSIS plus 1 plus IS times 1 over CS. And we factor it and make it simpler. We get this equation, and then we just move it, and the equation is IS equals to V over SR plus STL plus 1 over C. We can see that the denominator is like a quadratic equation. So next, the fourth, we from the previous equation, this is just an extra step. We can find the roots of the denominator of the S squared plus R over LS plus 1 over LC equals 0. We use the quadratic formula, which is negative B plus minus square root B square minus 4AC over 2A. And from the equation, we got that the value, and in the end we get S equals to negative R plus minus square root R squared plus 4L over C over 2L. Okay, next. We suppose that A1 and A2 are the roots of the denominator. So we need to we need to decompose the equation into partial fraction. So from the equation, we multiply both sides with s minus a1 bracket s minus a2. We get v over l equals to bracket s minus a2 a plus s minus a1 b. And we just use the both the roots. At s equals to a1, we substitute in, we get a equals to v over l, a minus a2. And at s equals to a2, we get b equals to negative v over l bracket a1 minus a2. And we just substitute it in from the previous equation, and we get v over l bracket a1 plus a2 bracket 1 over s minus a1 minus 1 over s minus 2, s minus a2. Okay, the last step will be we apply the inverse Laplace transform to the equation. So we also use the basic, we just use the properties, which is exponent to the power negative at is equals to 1 over s plus a. However, in this situation, we have 1 over s minus a. So we just change the negative to positive. We get e exponent to the power at, and we obtain the final current equation, which is final current general solution equation is v over l bracket a1 minus a2 times exponent a1t minus exponent a2t. And then I guess that's all from me. Thank you.
Okay, so for the simulation and analysis, we use Scilab to simulate the graph, to simulate the equation of RLC circuit. And this is the declaration of the variable. First, we did declare the parameters, initial condition, arrays to store result, initial condition, and Euler's method loop, update values using Euler's method, and then we calculate the voltage. Next, this is for the graph plotting code, and as you can see in here, the results of the simulation is a graph that shows the current in the RLC circuit. The first one is current in the RLC circuit graph, and then the second one is voltage across resistor, and then voltage across inductor, and the last one is voltage across capacitor. So all of this result shows that the graph has the voltage has relationship with the RLC circuits, and also we can see that it shows the second order differential equation of the RLC circuit, and also it applies the Laplace transform for the equation by using the graph results. So that is all for our discussion. Thank you.